You probably got my hopes up. I was very excited.
Okay, well, as far as I'm aware, Dr. Euler covered the underwater welding techniques with you at the last lecture, and I'm just left with a summary of the processes. So you can, if the welding is done in very shallow water, you can build a dam around the outside, pump the water out, and you can weld using dry welding conditions. That's quite an expensive method, but for places where pipes come on land, that might be the sort of thing that you do. You don't usually do a wet weld. You can run a welding torch underwater, but the quality of the weld is pretty poor. But there might be emergency cases where you would do that just to give you a short-term repair. Much better if you can have a small repair to do is to use a local dry chamber, which you can clamp and pump the water out and just weld in that small volume. So for localized corrosion repair and things like that, that might be possible. But it's small side only. If you really have to weld and repair something that's sitting on the seabed and you're in tens to hundreds of meters depth, then you might want to have a chamber where you pump out the water, but you still have the pressure head. So that's what they call a hyperbaric chamber. You can get good quality welds from that, but then you have to weld under high pressure conditions, and that's very hard, particularly on the welders. So you have to have good quality and welder performance assessments. And the welders have to be divers as well to do that, which is not always straightforward. And then finally you get a 1 atmosphere chamber, which is a very expensive way of doing the weld, but you can use the standard welding procedures for doing that. There are other things you could do. Here is an example where you actually just set the welding procedure up on the seabed. So we have this spar attachment system here. So this is the weld that you've got to make. Might be that you had to cut a section out to do that. This is sitting on the seabed. Everything's lined up there, and then you lift the whole thing out of the water to be able to do the repair. You might have a system where you have a pressure chamber loaded over the top here, but in some cases you can't achieve that, and you might want to lift just to check what's going on. But this is the normal sort of arrangement. You have this spar system which is loaded, you line up everything, and then if you're going to put your pressure chamber, you can put that down over the top. So this might be a sort of system that you've got on the deck. So the pipes would end up in here and in the other side, and they're all clamped together and they're held in place, so you can then do the welding by this process. And if the clamping is high enough, you can lift the pipeline up and as I say, weld at atmospheric pressure. Or you can have a system where that just aligns the chamber, which then goes down over the top of the system. So just because there's a chamber, it doesn't mean to say that's the only piece of equipment that you need to do the welding. So hyperbaric welding, using that sort of system, a couple of welders working with the normal welding processes that you see, but they're working at high pressure, so they don't have a great deal of time when they can produce good quality welds. got good sealing on the outside here. You'll notice that the concrete that's usually around the outside of this pipe that enables it to sink has been removed by this process. So that's something else that you've got to think about doing. Adds to the cost of these subsea welds. So you really don't want to do welding underwater if you can get away with it. For a tie-in like this you have to, but you'd rather avoid that. So here's a hyperbaric weld. And it's been done manually, so it's got a V preparation rather than the tighter U preparations that you'd see for the automatic welds. But it doesn't look much different from a conventional weld done at atmospheric pressure. So the actual weld metal freezing and microstructures you get are very similar. It's more to do with the skill of the welder and the welder being affected by the pressure rather than the actual intrinsic welding process. So you could do mechanised welds again, and if welder fatigue is a problem, then you'd like to set up as many mechanised welds as you can, and again hyperbaric systems, mechanised welding, they can be used to do. If you're really worried about these sorts of welder fatigues and the difficulty of handling things, and you've got just remote operation systems for doing it, then you might end up using systems like these, which are mechanical valves, which can be screwed onto the end of a pipeline, and then you just push the two parts together. And when you do that, when you slide this in, this sleeve comes back here and it lifts the blue parts out, so these grooves where things are actually locked together, and then you can slide the red part out. So if you put the red part on one pipe and the yellow part on another pipe, you could lock it together. In this country, this technology was developed very strongly so that people can take their gas cookers from one house to another when they move house. Instead of having to get a gas fitter in, you have these automatic systems where you can just manually break the connection. They're slightly more complicated than this because they tend to have no return valves built in them. So when you actually break the connection, a valve comes in and seals the gas. So these mechanical systems are very well designed, and they work very well after long periods of sitting around doing nothing. So if you've got a temporary connection, then you might consider these sorts of joints. Obviously, there's more of a risk of leak from this type of connection than a weld. So these are sometimes used when you're waiting for a campaign of welding to take place. And the other big problem that you find is that due to seismic activity on the seabed, the pipes have moved, so they no longer can be easily lined up. And then they have things like this weld ball system, where you can actually put rotations in to take the consideration that the pipes no longer can be lined up perfectly. And they've got sufficient flexibility inside that weld ball area to allow pigs and other things to go around the system. And these tend to be sleeves that go on the outside, so the pipe is put inside and then welded around on these areas. The weld ball allows for you to get the right sort of orientations, and when everything's sorted out, then you just weld that up as well with a fillet weld to lock everything into place at the far end. Not commonly used, but necessary in some circumstances. So if you want to summarise the offshore, S-lay systems for shallow water have a multi-station approach with multi-pass welding. Every weld is radiographed or automatically ultrasonic inspected. And we use some engineering critical analysis to decide whether the weld defects that you find are acceptable or have to be repaired. And we do that so that there's not so many repairs. On land we would probably repair everything. Offshore we would decide which ones to repair. J-lay, deep water, generally a smaller number of stations, but you're holding the pipes in the vertical orientation. You've got to have very good gripping to make sure that that's okay. Reel barge systems for smaller pipe diameters, very effective, particularly for pipe bundles. And sometimes you can have a barge that will take material from one place to another and then unroll it, and it's actually laid unreeled, and you might have some pontoons to actually float the system. That's okay for open water. It's obviously not okay if you're trying to actually get into the more complex systems where you've got lots of different assets, and you want to make sure that you don't collide with everything, and you've got to have plenty of space between the barges to be able to take this off. So normally you try to unroll where you can. Repairs are expensive. Repairs on the seabed are very expensive. Repairs on the seabed at great depth are incredibly expensive. So right first time and no repair is the mantra. It's almost impossible to achieve that, but when you're looking at probably £500,000 minimum for a seabed repair, you don't want to do it. You've got to have a good asset that you need for that. So subsea welding is usually hyperbaric welding. That means welder fatigue becomes critical. Just the same way that you have breathing conditions with different atmospheres of breathing and things for the welders to work at high pressure as if they were divers, then you have to consider that the attention span and the quality of thought is restricted. So there's a drive towards more mechanised welding processes which require less welder thought, I suppose is the best way to describe it. And the deeper you go, the more that's going to happen. And you have to have all the infrastructure, trained divers who can also be welders. You see that the premium for a trained welder is high, the premium for a trained diver is high. Put them together, the premium for a diver who's also a welder is very high. And these people are very highly paid, and that's part of the process. And if you're good at it, you've got a very good job, basically, for doing that. But there are very few people I know who can do that. Okay. So it talks about offshore welding, and I've highlighted the importance, while we're talking about that, of weld inspection. So I'm going to say a little bit more about general weld inspection in these processes. An engineer is only as good as his last failure. No engineer ever produces a totally perfect product that never fails. But it's what you do about it when it fails and how you trap it from failing in a catastrophic fashion that's important. So when we are going out and we're making this pipeline, it's a very simple structure of pipeline. It's a long tube with a few things dangling off the sides of it. We want to make sure that it works. And the best way to do that is to inspect it while you're making it and to inspect it while it's being used, so that instead of getting a catastrophic failure, you can stop things before that. So the whole point about inspection really is to stop the disastrous failure that you've got. And a disastrous failure might end in loss of life, or it might end in loss of money. The accountants tend to think about the second one, but most people surely would want to focus on the first one. So with a pipeline system, the pipe units that are produced by the pipe mills tend to be well inspected to start off with. And we talked about hydro testing and ultrasonic testing of the pipe segments. So you can make the assumption that as far as a pipeline engineer is concerned, the units that you're making your pipeline up from, the pipe segments, are probably in a good condition. So what you really want to do is inspect the bits that you did, which means inspecting the welds that you are producing to turn those pipe segments into the pipeline. And the weld inspection techniques range from the very simple, visual inspection, magnetic particle and dye-penetrant inspection, to the more complex radiography and the very complex, in theory, ultrasonic systems. And what those techniques do is ask two questions. Is there a defect, and how big is it? And to do acceptance tests properly on a weld, you need to know how big that defect is, because it's the size of the defect which decides whether or not you can accept it or not. And there are various different standards of workmanship and fitness for purpose that enable us to do that. So what we want is an inspection technique that gives us the size of the defect. And if that size is 0, that tells us that the defect's not present, so that's okay. Visual inspection. You are fitted with an incredibly good, very accurate assessment technique, and unless there are accidents, that assessment technique, your Mark 1 scanning eyeball, which most people have, is very, very good at picking up problems. You see things, your brain can interpret things much more than any automated, robotic, or technical system. What you can't do, though, is see inside the material. So visual inspection tells you what's happening on the outside. So that is an obvious defect. 2 pipe segments didn't line up correctly, so somebody tried to weld them so they would. And that was dug out of the ground, so you can see that the clamping was wrong in this case here. Looking at the colour of that pipe, I suspect it's a water pipe rather than a gas pipe. But I can't prove that. I was given this picture by somebody else from one of the inspection companies. And they said, you know, periodically we find things that you wonder how anybody ever got that accepted. Tends to be older assets. This one, because it's so black, it's been in the ground for quite some time. So it might just be that this is from that age when inspection wasn't so well done. Magnetic particle inspection systems, though, are routinely used, and that is because steel is ferromagnetic. So steel is a magnetic material. So magnetic particles can be used to identify defects in that steel if you make it part of a magnetic circuit. So this is a system here where we've got an electromagnet in this core, and there's a couple of legs which can be adjusted so that that gets into the surface, and then that couples with the surface, so you get a magnetic circuit that goes round that system. So you've got magnetic field lines that are going through the material between the two legs that are in contact with the pipe. And it's been painted white so you can see the magnetic particles when they're added. So what happens is you get these magnetic field lines that run through the material. And in an ideal case, where there's no defects, they will be within the material and very little escapes at the surface. If there's a crack, then we get what are called fringing fields, these magnetic fields which come outside of the material and flow around the crack, because there's this non-magnetic anomaly there, and the magnetic field lines have to close. So if you then spray a magnetic particle onto the surface, so an iron particle, they will tend to collect where these magnetic field lines come up over the surface. So if this crack is there, you'll get the magnetic particles collecting on top of the crack. The magnetic field, as I say, is normally electromagnetic, but it could be a big permanent magnet. The prods, the legs, and the cable to the power supply are really the only things you need. It's a very simple piece of kit. A bit of white paint is quite cheap, and being able to spray from an aerosol can some ferromagnetic powder means that you can do this thing on site, and you can test welds in complex shapes. So here is a T-piece being welded on with a shell structure, and the welds are being inspected to look for cracks in this A sort of variant on this, which is better for non-magnetic materials but can also be used on magnetic materials as well, is dye penetrant inspection. So dye penetrant relies on the fact that if you've got a crack or a crevice, a low viscosity liquid will be drawn into those cracks and crevices by capillary attraction. So if you coat the whole surface of your component, you can see there with the red dye, wash that off and then spray it with a chalk-based absorbent paint, that paint will sit on top of this crack. The crack's got the dye in and the paint is absorbent, and it will suck some of that dye back out of the crack and leave a red mark on the surface. And I mentioned you need to be able to measure things. You can measure the length of the crack just by putting a ruler against it, which is very useful. So this is a commonly used factory inspection technique. You know, the skill level for the inspector is pretty small. They need to be able to paint things, and they need to be able to read things off with a ruler. The key thing is leaving it long enough, a few minutes as it says here, for the paint to be sucked out so that you get these marks. If the surface is very rough, you can't always see it, but painting it white with these spray paint systems gives you a fairly good visibility of what you're looking at. But that only tells you what's happening on the surface. Yeah.
This dye penetrant, these paints are inflammable?
Once the paint is dried, no, they are solvent carrier systems. So yes, the solvent is flammable, so you need to do it in a ventilated environment. They are generally carried by fairly thin solvents that evaporate quite easily. So the big problem I find is not so much the flammability of the solvent, but the fact that you could have the solvent affecting the workers. Smelling too much of this solvent, they get a bit sort of high, and that they can do some silly things afterwards. So I wouldn't recommend doing dye penetrant down a hole unless you ventilate the hole in some sort of way. Not usually a problem with storage and flammability, because they come in small cylinders that you can handle normally. I can't think I've heard of anybody. Well, apart from the company where their factory burnt down and the solvent store went up and all the dye penetrant went up with it as well, but that was an external fire to the factory. So yes, storage of the material, I think you do need to be careful about, but use of the material isn't a problem. Okay. So those techniques I've talked about so far mainly give you things about what's on the surface. But unfortunately, in the real world, particularly the multi-pass world, it might not be the surface where the problem is. So you then have to have ways to inspect the material that can see through the metal and look at what's happening under the surface. And the obvious way to do that is radiography. And radiography simply is just like having an X-ray taken of your body. So you're looking for variations in density of the material that you're seeing. So you put an X-ray source into the pipe generally, or as we'll see in a minute, on one side of the pipe, and then you actually put a film or a detector on the outside of the pipe or on the other side of the pipe, and you look for variations in X-ray intensity that makes it to the detector. And if the pipe is complete and there are no defects, there's a lot of material to absorb the X-rays. If there are holes and pores, there's less material to absorb the X-rays, so more X-rays will make it to the film. So on the film, things go dark generally when there's a defect present in the system. So a couple of internal sources. The sources act like point sources. So here's your pipe specimen, there's the source, and you get this cone, and then on the detector you expand things a little bit. As we've drawn it there, the detector is a long way away from the specimen, but often we put the specimen as close to the detector as we can, so that we can get a more realistic measurement of distance of size. So if you want to use this technique to measure the size of defects, you have to calibrate for the distance between the film and the material that you're measuring. That's something that you need to be aware of. So here's a very simple case, what we call panoramic X-ray inspection. The source is right in the middle of the pipe, and the crawler's designed to make sure that that source is effectively right in the middle of the pipe. And then you find where the weld is on the outside of the pipe, and you place a strip around there which has the film. So you get full 360-degree inspection of the weld from the source coming outwards. And that's very simple, but you've got to be able to have a nice crawler inside, so it tends to work better for bigger pipes.
Sorry, the crawlers, are they specific for different diameters, or they can expand for different diameters?
Both are true. There are specific ones. If you've got a regular inspection of a pipeline of a certain size, you might have a specific crawler for that size. On a pig, you might have an inspection station that fits exactly that pipe size. If you contract somebody else to come and do the measurements for you, they might have a multi-purpose crawler where you can change the sizes. So you can do either. Qualified radiographic interpreters. This is another skilled job that you need for your pipeline if you're going to use radiography. You've got a person who takes the film, who develops that film, and then looks at that film on a light box or on other systems. These days they tend to be scanned into computers, and you look at it on screen. And you have to make sure it's calibrated, and you know all the sizes and all the positions and things, so that you can measure the lengths. And then somebody with skill then looks at them and says that's a defect of that type. And I'll show you some radiographs later on that have different types of defects in, and you can see that some of them are easy to spot, and some of them you need quite a bit of skill to be able to do it. And I know from the ones that I've seen that the defect is there. It's much more difficult to see it if you don't know the defect is there. And that is the really difficult part. With modern electronic detectors, which you can have in some systems, you don't have to film, and you don't have the guy measuring it with a ruler. It can all be done in the computer. But that's not so easy to apply on a site welding situation. So there are still people that use films all for everything. I'm afraid my pictures are all old, so you'll only see what used to happen, not necessarily what's happening in today's environment. So, just as an example here, we've got lack of penetration. So you can see the weld design at the moment. The capping passes and the filling passes have been done well, but the first pass didn't completely melt the root. And if you look at a radiography result, you can see that we've got a nice weld here, and then there's this dark line down the middle of the case where it's passed through more air, so there's less absorption of X-rays. So that dark line tells you exactly that's where the lack of penetration is. And it's right down the middle of the weld, so pretty much that would be a root pass effect. And we'll look a bit more about other types of defects later on. You can't always get what you want. You can't always put a crawler down a pipe. Sometimes you can get somebody in for a short distance away from the front end of the pipe to actually put some film over the weld, and then you can use an external source to actually show up the defects. So this is a single wall, single image case. And that means if the source is on this side, you're getting images on the film here, and then the X-rays are then passing through, and you're getting images on the film on the other side as well if you're not careful. Obviously, you need to know what the focus to film distance or source to film distance is, and the defects that are on the front end of the pipe will be much more apparent than the ones that are on the back side of the pipe. So you might have several source positions to do that. Obviously, you need access. If you take that a little bit further, you can put the film on just the back side of the pipe, and you can, from a single source angled to the pipe, you can actually capture on one film what's happening on the front wall and on the back wall of the pipe. So if you looked at that like so, this is a straightforward case. The defects in here are being tested, and the defects in that larger range are being tested. But both, in both cases, the X-rays pass through two lots of wall, and then you get an image from both sets of defects on one plate. And if you offset that, you can make it more likely that you'll separate the defects from the front end and the back end, in that they're spatially separated. Since we're only looking at a weld which goes round in one circle here, we can spatially separate the weld from one side and the other side, so we can move the front end to one side and the back end to the other side for doing that. This is only really applicable when you have no access to the inside of the pipe. So you've got options to do with that, depending on what sort of things you can actually do, given the pipe job that you're working on.
Excuse.
Yeah.
Yeah, for the internal testing, when you're taking the X-rays,
Yeah.
do you put the pipeline offline? Do you put it off, or you maintain it running?
All of these, when you've got an X-ray source in the pipe, there's no gas. Your X-ray is a high voltage source. There's easy possibilities of sparking, so the pipeline's out of service when this is happening. From the external cases, like here, you might get away with using it with gas. The X-rays don't see the gas. So, you know, for a fully external analysis, you might get away with it with the gas running. And I know that has been done. But for an internal source, it's always gas-free. So here's that double wall, dual image situation with the offset film we've seen before. The X-ray source has some slits in it, which will dictate which direction the X-ray beam actually goes. So we see this angle of X-rays here. That's defined by basically having a hole which those X-rays come out with. So you surround the X-ray source with an absorbing steel box with a small hole in it, and then you have a bit further out, you have another slightly larger small hole that defines the cone angle. So by controlling really the absorption of X-rays before it gets to the pipe, you can control the beam of X-rays that's coming through, and then you can use that to look at different parts of the system. So here's a weld that we're looking at, and the double wall image, you can see two sets for the weld. So one's offset from the other. So you can see here, there's one side here, and there's the other side here. And there's defects, in this case, poor porosity in both sides of the weld. So you know that that's a uniformly bad weld all the way around. So radiography has been used for many, many years because it's cheap. Permanent record X-ray films don't disappear immediately, but they degrade with time. So there are some companies that still have X-ray records of their original radiography, but if you pick them out of the records now and you bend them a little bit, they will fragment into pieces because they've become embrittled. So some companies have been scanning their old data just so that they can maintain full record. So it's only really semi-permanent. Photographic film doesn't last 40, 50 years. And as companies stop making photographic film, although the companies that make X-ray film still exist, you can't buy 35mm film from Kodak anymore. You know, Kodak became an electronics company, not a film company. So you know, you're not going to get standard film in many cases, but electronics detectors do exist which enable you to do that. Get into gadolinium futures. One of the few applications of gadolinium as an element is in X-ray cameras as an absorber behind the film. So it's a nice thing to do if you've got a source of it. So radiography is good for defect identification, it's good for length sizing, but it doesn't tell you very much about the depth of the defect. You'll see the length of it quite clearly in the image, but you'll just get a black line, and it won't tell you whether it goes through the whole system or it's only in one part of the world. In fact, the usual assumption is it's one part of the world that's affected, not the whole world. And that's occasionally a dangerous assumption. It's a relatively slow process. You've got to wait offline while somebody develops the film, or you've got to wait for somebody's computing abilities to be able to let them analyse and measure. It's not an automated measurement system. That's always a qualified interpreter. And you can miss cracks and lack of fusion that are what we call tight. So if you imagine, if you've got a big open space, the X-rays are coming through, so you've got a big open space, there's no absorption in that big open space, that will give you a difference in intensity. If the crack is very narrow, it only has a small path through the open space, there's very little detectable difference in intensity under those cases. So going across a crack, you don't see much. Going along the length of the crack, you tend to see more intensity. So you've got to be very careful about which orientation the material is. And I've said X-ray all the time because X-ray is generally better than the other possible source of radiation that does radiography, and that's gamma rays. But that means you have to carry a nuclear source around with you, which is not the world's safest way to do things. But you don't need a power supply. So, you know, there are pros and cons. But there are safety implications for all of these processes. X-rays are ionising radiation, gamma rays are ionising radiation. There's a limit to how much the workers can be exposed to these sources, which is the same way as if you go into hospital and have a chest X-ray. You can't have one every hour. You soon get over the exposure limit. And secondly, for the old film systems, certainly, you have chemicals that you have to make up and dispose of, and the fumes from the chemicals can also affect the technical staff that are working on that. So you need to be a bit careful. Modern computer systems, much less so. Ultrasonic systems are also very commonly used. Manual systems are largely used for corrosion monitoring, but they are also used occasionally for weld monitoring. So the idea is that you have a transducer, which is an ultrasonic crystal which is vibrated by an oscillating electric current, or a voltage, an oscillating voltage across it. And those vibration pulses are acoustically coupled into the pipe, so you have some sort of contact, some sort of medium to take that vibration and translate that to vibration in the pipe. And then you get a sound wave that goes through the pipe, and it's reflected back off the back side of the pipe or off a defect, and you then detect the reflected or transmitted sound, and by looking at the time of flight you can then detect different types of defect, different types of reflections. So here's an example. This probe, you can see the probe's at an angle, so we're actually scanning this weld because it's coming in at an angle like you can see at the top there, and depending on the distance from that weld you can go through the thickness of the system, and you get a complex picture like this where you'll get a main peak here. This is probably the peak that's associated with reflection off the back surface, and then there might be some other noisy peaks there as well, and then there are some other defects in here. So you get a bit of a mess, and again a skilled interpreter can tell you, oh, there must be a defect, lack of fusion or something like that. It's notorious, manual ultrasonic, for inspector fatigue. In the same way we talked about welder fatigue in hyperbaric welding, you get inspector fatigue in manual UT, where you'll get good performance at the start of a shift, and as the shift goes on, things get missed. And that's why we want to automate these processes. But it can give you, in principle, defects at any depth, depending on the angle that the transducer works at. And it can work on site. It's very widely used for looking at lamination defects, which have been introduced during the rolling process. So if you put the probe on the surface, a 90-degree probe, you scan the sound down, it bounces off the back face and then comes back up, that's good. If it scans down and finds a lamination halfway through, you measure effectively half the thickness of the pipe, or whatever. And at that point you can reject the pipe. So on site, I think the main use of these manual tests with this simple compression probe is for looking for these laminations, just so you can reject a pipe segment. You can have lots of defects in lots of positions, and that's where an automated system can tell you a lot more about it. So here is a mechanized weld in a badly fitted up system, and you can have lack of fusion pipes in the root regions here. You have lack of fusion, in fact, anywhere in that system. You can see these height mismatches, you can see different amounts of weld metal are deposited, so the offsets of the weld metals, all of which can have an effect on the overall response. So instead of collecting the data from one position in the weld, you might want to collect the data at this height, at this height, at this height. And if you know what the welding procedure is and how many weld passes and how thick each pass is supposed to be, you might be able to set up an automatic system that interrogates each of those passes. And that's why we go for automated systems, because it gives you much more information about all parts of the weld. So how do we do that? Well, we have really a different detector for each part of the weld. So the transducer and the receiver have an angle, and the sound wave can bounce off the root pass and come back down. Slightly closer, slightly different angle, we get a bounce of that sound wave off the back of the pipe and then up to a defect perhaps in the hot pass. And then we can have separate transducers and receivers where the bounce pattern for the sound waves can be from the different passes up through the system. And then you might have an even further spaced transducer receiver which has a bounce and then comes up from the top. So by designing the right transducer and receiver positions in an array of transducers and sensors, then you can have signals that come from each part of the weld that can be separated, so that we don't get, two sets of positions contributing to the same output. And that enables us therefore to measure particularly lack of fusion defects of different passes and do them all at the same time with one large array of sensors. And that's why you get something like this. So you can see transducers and receivers, and lots of different ones. Some of them are separated, some of them are close, some of them are together, and then there's wrapping around the pipe, So there's an awful lot of sensors and transducers in one process. So you then clamp that, this goes down and it goes around the pipe, and then you fire it up and you get a lot of information, and then you have to process it. The other thing you can do is have like a cart, what we call a phased array, and we only have a few sensors in this case, but we're measuring continuous variations as you go around the weld, and then we're looking at phase changes between the ray that goes out, if you like, the sound wave that goes out, and when it comes back. So you're interfering the two, and you're measuring phase differences, and that gives you an indication of the scattering that's taken place on the way. So that's a much simpler sensor, but you're relying on that moving and collecting lots of information as it moves to give you the results. So that's another fixed array system. Loads and loads of sensors, loads and loads of wires, lots and lots of signals coming out, lots of interpretation for you to do. So these are things that specialist companies produce, and they optimize exactly for a particular job. And that's the plan for that particular array of sensors. Got 3 sensors on each side of the world with different angles, and they're looking at 3 different parts. You've got time of flight probes, and you've got phase probes, and you've got detectors where you're getting a different signal coming back, and detectors where you're getting the same signal coming back. In this case, this setup relies on you having a transducer one side of the world and a detector on the other side. So it's completely separate transduction and receiver. Other people try to use the same sensors, and there are advantages and disadvantages to each. So it's really quite common. So they are piezoelectric. That's what PE stands for, probes. Piezoelectric material, if you apply a voltage to it, it will contract. And then if you apply an oscillating voltage to it, it will contract and in an oscillating fashion. And that's like providing a wave of sound hitting the surface if your frequency of contraction is correct. And the speed of sound in a material depends on its Young's modulus and its density. So if you've got a fully dense material and you know its Young's modulus, you can work out the speed of sound, so you can work out the probe frequencies that you need quite easily. Second system here, this is one of the phased array systems. You can see there's a track and there's a detector, and that detector is crawling its way around the track. So in theory, the detector is simpler, but the processing is quite a lot more complex. And that's the picture that we had before. And now you're seeing these arrays here, and you're looking at the different reflections coming back, and then the phase differences that you would expect from the detector here and the detector here to give you the positioning. So depending on which detectors have signals arising, you can see which phase difference, and that tells you which angle it was at, and then where the defect actually is. So what you get from these systems is quite a lot of information here. So you can see here roots, and then the hot pass, second hot pass, in this case filler passes, and you're looking for the signals coming higher than you were expecting, and you can see there's quite a lot of signal in this region here, and that's telling you that there's a lack of fusion defect within this material, and it does that for it in an automatic way. If you look at this case here, on this side, there's very little of that, so this is actually a good weld. So normally what you would do with these systems is have some sort of calibration, so you know what sort of signal you're looking for. So you make welds where you know there's lack of fusion, you set it up, you look for the signals that you get, and this is measuring both sides of the welds. This side is good, this side is not, and that's typical with a lack of fusion where the cart is over to one side of the preparation when you're doing these automated welds or mechanized welds. So you can get quite a lot of information. There's quite a lot of stuff being printed out. Time of flight will tell you about laminations and things like that as well. That's there. This then has a red bar which tells you when it thinks something needs repairing. So you've even programmed in the failure criteria in this case. Now, doing it on site requires one extra thing that you do, because these ultrasonic systems and the speed of sound in material is temperature dependent. So you have to calibrate and set up the machine on the site on the day you're doing the measurement. So you have this thing here, this is a calibration pup. So this is a piece of the same steel that you're making the pipe, with known thickness and known curvature and known defects, may even have a weld in it of known properties that you've already measured before, and you set the machine up using that to start off with before you make realistic measurements in the field. So calibration of these detectors is very, very critical, and it has to be done under field conditions. So that's another part of the process. So given the time, I will stop here for today. So what I want to do next week is finish off the automated inspection and talk a bit about engineering critical analysis. And then we'll go on and I'll show you lots and lots of pretty pictures of different types of defects in radiographs, so you can see how complex it is to do that. And then hopefully I'll be able to canter through very quickly the repair sections afterwards. My plan is to try and finish everything before Christmas. I don't know whether Professor Gibson has finished his lectures yet.
Maybe Friday.
Yeah, okay. Well, if so, I'll use his lecture slot just to finish off after he's finished his ones, just to make sure we can get everything done in time, so that everything will be done before Christmas. But really what we're doing now is I'm just showing you lots of examples, so it shouldn't be too complicated. It's just I need a bit of time to actually get through them. Okay?